Hello, everybody. Welcome back to class. Tuesday, our first day of the week. How's everybody doing? Can you let me know who's here? Say hi to me. Say hi to me, please. Navik, Jax, hello, hello. Jared and Turner, right on time. Good to see you. Max, Inman, hello, hello. Sam, welcome to class. All right, well, it's 10 o'clock. We can get started with the important parts of today, which is the simultaneous sip. So if anybody has their coffee or water, juice, milk, chocolate milk, whatever, and would like to join, now would be a good time to do so. All right, so let me see in the chat who joined in on the sip, and then we could get started. Molly has an emoji prepared, it seems like. Well, a lot of sips today. A couple of emojis. Nice, nice, nice. I'm glad we still have a little bit of enthusiasm. Okay. So the plan for today is we're just going to do a few more examples with optimization. All right, so I'm going to try to give a good amount of time for each problem for you to think about it, but it's a little awkward with the me not actually seeing any of you. So I guess we'll just try to go one step at a time. I'll write out the question. I'll give you a minute to try to get it started. Then we'll catch up, and then I'll give you some more time, like that. All right. So we'll make it work. We'll make it work. So the first example is find the area of the largest rectangle that can be inscribed inside a semicircle. Inscribed inside, that's repetitive. Inscribed in a semicircle of radius r. Okay, so I'll draw the picture and label some variables, just so we all have the same vocabulary or same variables going on. But then I'm going to ask you to find what function are we trying to optimize and what constraints do we have. Okay, so that's where we'll start. So I'll give you a minute to figure that out. Then we'll catch up, and then I'll have you go on from there. Okay, so just to draw the picture, we have, let's say here's the XY plane. We have a semicircle with radius r. And we have a rectangle inside of it. Okay, and we'll say that the height of the rectangle is y. And for the sake of making this question easy for us, we'll say it goes over x to the right, and it also goes over x to the left. That will make the question a little bit easier than having x be the entire length. Okay, so we have a goal. We're trying to maximize something, and then we have constraints. Okay, so I'll give you, let's say, a minute to think about this, and if you have a guess or some ideas, just feel free to put them in the chat, because your classmates will probably like to see them also, if they're helpful. I think you want to optimize a equals 2xy. Good, but optimize means either find a max or a min. Which one are we trying to find? Max or min? All right, we want to find the largest. So largest would be maximum, right? Okay, now here's the hard. Not that what you said, Jax, is not hard, but this next step is a little bit harder. What are the constraints? Anybody have any ideas? Let's say this was on a test or a quiz, and you're looking at it. What would you do to just guess? And it's okay. Wrong answers are fine. Makes me see that you're trying. One half r squared. 1/2 pi r squared. So that's the area. I mean, so that is technically an upper bound for the largest it could possibly be, but we can't have, right? Our rectangle can't kind of become a semicircle, unfortunately. But that's a good idea. We have this bound where we have to lie inside of this circle, right? This circle has to play a role in our solution at some point. Okay, let me see if I could lead us in the right direction. Does anybody know what the equation of this curve is? What is the equation of the boundary of a circle? And I'll just fill in the blanks slowly. All right, a little bit more is coming up. Yes. Yeah, so the equation, right? The equation of an entire circle, I'll draw it over here. Right? The equation of an entire circle, I'm going to erase this eventually, but is x squared plus y squared equals r squared. Right? I'm sure you had that in Alex. Right? X squared plus y squared equals r squared. These are all the points that are r away from the origin. So if we wanted just the top half, we solve for y. And so you get y is equal to the square root of r squared minus x squared. Right? To get the whole thing, you'd have a plus or minus. The minus would be the bottom half. The plus is the top half. So we have this constraint that y is equal to, right? Our y value is going to be a point on the curve, depending on our x value. So our constraint is that y has to equal the square root of r squared minus x squared. Okay, and there's one more constraint that we have to consider. X, we're saying, is how much we go in this direction. Okay, so x has to be positive. Right, because if we picked it to be negative, it'd be the same. It doesn't. If we picked it to be negative, then it would correspond to the same rectangle as when it's positive. Doesn't make any sense, or not necessary. And the largest x could be is r. If it was any bigger, it would be outside of the circle. Okay, so we want to maximize the function. R is just a number here. It's not a variable. R is a constant. So we want to maximize 2xy, where y is equal to the square root of r squared minus x squared. And we have a domain that's a closed interval. Okay, so my question before we keep going on, I know we're going a little bit slow here, but this is important. How do we find the absolute max of a function if we have our domain, if our domain is a closed interval? So what do we have to check? Where can the absolute max occur if our function is continuous and its domain is a closed interval? Right, another way to write this is like x is in 0 to r. Find where the derivative changes from positive to negative and the endpoints. Yeah, so we want to, another way to say that first part is we want to find the critical numbers and we have to test the endpoints. Okay, so yeah, for the max, to find a max, you're right. We would have to find where not just the critical numbers, but the ones that go from positive to negative. But if we just find all of the critical numbers and plug them in, whatever one gives us the largest will be the max. Okay, so we find the critical numbers and the endpoints. Okay, so that's what we got to go with here. So let's see. So really what we want to do is maximize the function a equals 2x square root of r squared minus x squared on the domain 0 to r. Okay, so again, we'll take the derivative, find when it's 0 or undefined, and also test the endpoints. Okay, so I'll give you a couple minutes to think about this. Yeah, let's say a minute to try to work out this derivative. Minute to minute and a half to work out the derivative, and then we could all catch up. All right, but please put any comments you have in the chat. So something you could answer to maybe help out your classmates that aren't sure where to get started. What rules do we have to use in order to take the derivative of this function? So what rules are we going to use to take the derivative of 2x times the square root of r squared minus x squared? Okay, so we want to take the derivative, and maybe everybody was focused on solving this by themselves, that they didn't want to answer my question. You want to take the derivative of a product. So we're going to need the product rule, right? So a prime is equal to the first, which is 2x, times the derivative of the second. Bring the 1/2 in front. Drop 1 from the exponent, and then multiply by the derivative of the inside. So that's the first times the derivative of the second, plus the derivative of the first, which is 2, times the second. Okay, and now let's see what this simplifies to. So the 2.5 cancel. We're left with negative 2x squared over r squared minus x squared to the 1/2. Plus 2 r squared minus x squared to the 1/2. How do we simplify this? Or do we have any questions about the derivative that I took? All right, so my question is, we have a fraction plus some other term. And eventually we want to find when it's equal to 0 or when it's undefined, right? So don't we want to get a common denominator? So our common denominator will be the square root of r squared minus x squared. Right, and this, the square root of r squared minus x squared times itself, the squares cancel out, and it's just raised to the first power now. So our numerator becomes, well, we have minus 2x squared plus another minus 2x squared. We have minus 4x squared plus 2r squared, and our denominator is r squared minus x squared to the 1/2. Okay, somebody literally say anything. I'm not even sure if the chat is broken or not now. All right, Turner, you're okay. All right, Sip, good. Are we considering where the function is undefined as critical numbers? It works just fine. Okay. Are we considering where the function is undefined as critical numbers? Well, no. Where the function is undefined, that helps us give us our domain. Okay. The critical numbers will be when the derivative is undefined, and so it happens that one of those points also lies in our domain, or is one of our endpoints, and that's fine. So it just means we have one less point to test. Yeah, so let's just, and if our critical numbers are out of our domain, we don't have to we don't have to care about them. But yeah, we still have to figure out when our derivative is 0 or undefined, just like we did in the past. So let's start with when it's 0. So a prime equals 0. That implies that our numerator is 0. And when we solve for x, we get x squared is equal to r squared over 2, or x is equal to, now sure, we'll get plus or minus, but the minus term will be out of our domain. So we'll just have r over root 2. Okay, and now let's find when our derivative does not exist. That tells us that our denominator is 0. That happens when x equals r. Again, it would be negative r as well, but that's not in our domain. Okay, and so now what we have to do is just evaluate our function at both endpoints and all of our critical numbers. Well, one of our endpoints is a critical number, so we just have to evaluate our function at 0, r over root 2, and r. Okay, and so while I'm doing this, please ask any questions you may have. So our function is 2x times r squared minus x squared to the 1/2. So when we evaluate at 0, we get 2 times 0 times r squared minus 0, which is 0. And I erased our drawing, but that would mean that was when our rectangle would just be a vertical line. So there's no area to that. So when x is equal to r over root 2, you have 2 times r over root 2 times the square root of r squared minus r over root 2 squared. Which, believe it or not, works out to be r squared. Okay, so you could do this algebra on your own if you'd like. And the last point we have to check is the other critical number, which is also the last endpoint. When x equals r, you get 2 times r times the square root of r squared minus r squared, which is 0. Okay, and so the question wanted us not to find the dimensions, but to find the largest area. So the largest area is r squared. Okay, so I'll give you a minute to kind of write this down and ask any questions you may have. This was a really hard question. We had to, figure out what the equation of a boundary of a circle was, which had to dig back into our memory. And then we had square roots and product rule, chain rule, and all that stuff. Endpoints we had to test as well. So in these optimization questions, if you have a closed domain, you still have to check the endpoints. But yeah, I mean, all the process is exactly the same for these. Figure out what we want to maximize, figure out what the constraints are, and then find the critical numbers, check the endpoints as well if we have endpoints. Okay, so again, ask questions if you have them, but we'll move on to another example. I have an example worked out. I have an example worked out in the notes, which I have to post. That deals with economics, but the question's long and we don't have a lot of board space, so we're not going to worry about that. So we won't have any economics type questions on a test or a quiz. But if you are interested in economics, it's like a supply and demand type question. If you're interested in that kind of thing, take a look at the notes, because there's an application to economics there. Okay. So this question says, if 1,200 square centimeters is available to make a box with a square base and open top, find the largest possible volume. Okay, so again, I'll sketch a picture. I'm not sure if that picture is good at all. It's not very good, but the idea is we have X, Y. We have a box with length X, Y, and Z. And the top here it's like an optical illusion. Yeah, better. Okay. The top is open. Okay, so my question for you is what are we trying to optimize and what are the constraints? Okay, so we'll say the bottom is the bottom face is this XY face, and the top would be the other XY face. Okay, so we want to minimize or maximize some function with some constraints. What is the function? What are the constraints? Yeah, good. We want to maximize V equals XYZ, right? That's the volume of a of a rectangular box. And what are the constraints? Well, we have a square bottom. So two of the sides are equal. And the surface area has to equal 1200. Okay, so well, we can replace the y with x because it's a square bottom. Okay, and our constraint. Okay, so we'll say the bottom is the x by x face. So we have this the sides of our box are x by x. Here's me unfolding the box. Right, since there's no top to the box, I unfold it. There's one x by x face, and there's four z by x's. So x squared plus zx equals 1200. And so we could solve for z. we get 1200 minus x squared all over x. Okay, so our function we're trying to maximize, the function we're trying to maximize is really v equals x times 1200 minus x squared over x. Which simplifies to 1200x minus x to the third. Oh, sorry. I didn't see your question. Why is there only one z? Why is there only one z? Oh, okay. Yeah, good call. Because I made a mistake. Plus 4zx. So when we solve for z, we should have an x down here. Good catch. That gives us a 4 here. This becomes 300. And we have it over 4. Okay, sorry about that. Good catch. Just, I did that on purpose, making sure everybody's paying attention. I try to, when working out these examples, I try to leave the notes away from me so you could kind of hear my thinking process while doing them. But the downside to that is what we just had here. Sometimes mistakes are made. Okay, but we recovered. Yeah, so we want to maximize this function. So let's take its derivative. So that's 300 minus 3x squared over 4. And we'll set it equal to 0. Okay, so we get x is equal to plus or minus 20, but it doesn't make sense to have a negative length for x, so it's just positive 20. Okay, and so we know x and we know the volume as a function of x, so we could find the volume, right? Because our question said find the largest possible volume. Our answer should be a volume. So the answer is v of 20. Which is 300 times 20 minus 20 to the third over 4. And when we work it out, we get 4,000. And our units would be cubic centimeters, right? A volume would have degree 3 for its units. Could you also plug x into the constraint equation and then do v equals x squared z? Yeah, so you could use, you could plug x equals 20 into here, and you would get whatever that works out to be. So let's see what that works out to be. 1200 minus 400 over 80. Which is 800 over 80, which is 10. And then, yeah, you would do v equals x squared times 10. So 400 times 10 is 4,000. So yeah, that's another way you could do it, Jax, if you wanted to use this equation. Okay, let's look at one last quick one. End on a positive note. So the sum of two positive numbers is 16. What is the smallest possible value of the sum of their squares? Okay, and just since we're kind of short on time, I'll write out what we're really trying to do. So our goal is to minimize the sum of their squares. So we'll say the positive numbers are x squared plus y, or x and y. So we want to minimize the function, which I guess we could give it a name. We've been using a lot, so we want to minimize this function a. I don't know what a stands for, but it's x squared plus y squared. And our constraint is that the sum of these two numbers is 16. And we could also have a constraint that says they must be positive, and we could just throw out the negative numbers we get as a solution. So the constraint is that x plus y is equal to 16. Right, and so like we do with all these questions, solve for one of the variables in our constraint equation, and then plug it into our function we're trying to minimize. So really, this is saying that y is equal to 16 minus x. And so we have this function that we're trying to minimize, which is x squared plus 16 minus x squared. And we might as well multiply this out just so we don't have to deal with the chain rule or anything. X squared plus x squared minus 32 plus 256. That's 32x. All right, now let's take its derivative. And set it equal to 0, and we can solve. We get x equals 8. Okay, and so how do we want to find what is the smallest possible value of their sum. So we want to find like what the sum of their squares is. So we could find y and plug it into here. Or we could just plug our x value into this expression here. So a of 8 is equal to 8 squared plus 16 minus 8 squared which is 128. Okay, so this one is pretty straightforward. I guess we should be careful, right? Because like the reason why it worked out so nicely was because we wanted to find the minimum, and when we took the derivative, it gave us a minimum. But if it wanted us to find a maximum, we'd have to check the endpoints of our domain. So what's the domain of this function? Right, because technically we should still be checking the endpoints of our domain. Well, let's see. The numbers are positive, right? So that means x has to be greater than or equal to 0. And also y has to be greater than or equal to 0. So the largest value x could be is 16. Right, and now we should check our endpoints just to make sure we actually did get a minimum. And we did. Yeah, 128 is smaller than 256, both times. So yeah, so if this question was rewritten and said find the largest possible value of their sums, 128 would not be the answer. We would have to check the endpoints and we'd get 256. Okay, so that's all I have for today, but I'll stay around to answer some questions if anybody has any questions. The quiz on Friday, and I'll email you. The quiz on Friday will be on optimization, or Thursday. The quiz on Thursday will be on optimization. So I'll give you some practice problems for that. Yeah. So ask any questions you have, but if not, you know the drill. Make sure you hit the like button on the way out. We got to get to 1,000. We're so close. We're so close. Yeah, I got office hours again at 1 today. Yeah, I don't know. That's it. Yeah, email any questions you have about the test, you can just email me. The quiz is on Thursday this week. Yeah, Jared, we don't have class on Friday. It would have been a traditional traveling day, but yeah, we don't have, nobody travels, but we still no class, I don't think, right? There's no class on Friday. Are the simulation questions and web assigned still extra credit? Yep, they will be for the rest of the semester. So if you could get them to work, great. But if not, no big deal. All right, well, if there's no more questions, I'm going to end this live stream. We'll see you all tomorrow at 10 o'clock. Bye-bye.